Should I start? Oh.
Anyone else?
That's the common head.
Roger, right?
Yeah.
Check the mic as well. This is me. I think we were supposed to be the chair of the thesis defense that's happening now. Is that right? See, classroom and comp available. Okay, thanks so much. So Roger, we got to put the next calendar.
Okay.
Animesh, did you print the form?
We asked for this thing, yeah, but we can be here, right? So we don't,
Yeah.
let's not do any further.
Yeah. I'll get some.
Prasad, can I have you with you?
Okay. Yeah, just,
Thank you.
thanks.
Okay, welcome everyone. And today I'm going to give my presentation on my thesis work, which is structured information extraction for scientific documents. And I hope by end of today, you will know more about scientific document processing and maybe even start working on scientific document related work, tasks. So why do we care about scientific documents and why do you want to do structured information extraction? So simple one-line answer is too much information. But if we want to go into more details, the idea is that scientific document is essentially a repository of our combined knowledge. It has almost most of the information, but in more structured and formal way. And it's usually difficult for human to interpret large patterns by just looking into one or few papers, which they read, let's say, in a week or over their lifetime. So we want machines to be able to combine large source of information, process it much faster, and give us more insights. Many of these challenges have been recently taken up because the speed of processing of documents have become quite fast these days. So one of such application is Big Mechanism project, the idea of which is funded by DARPA. The idea was that it will learn all the literature on cancer and try to identify what are the potential cures for it, because there has been years of research on it and no human can effectively read more than thousands of paper to form a overall idea of how the landscape of cancer medicine looks like. So what we are doing is looking into the more ground level work for this, how to do information extraction such that it can help these all top level tasks effectively. The particular problem statement that we would be looking into this thesis is information extraction from different contextual size. So the question will be, what is contextual size? Contextual size is the amount of text required to do information extraction for this particular task that we would be talking about. So we'll be dealing with certain number of tasks. We'll be seeing how much information in terms of text is required to do information extraction. And that will be the main driving factor. So to give an example and to put it in terms of scientific document, this is one of the scientific document. So one of the context example is short, which is reference string. So reference string is essentially a single string or a single statement, which is used to credit someone's work. Essentially, if you want to do information extraction, you don't need anything other than the reference string itself, which is a short context. Similarly, medium context can be one paragraph or collection of few paragraphs or collection of few sentences. There are many other substructures in scientific documents like author affiliation or equations and diagrams, as well as tables. There are a lot of research going on in these areas. For example, some researchers at LNAI are trying to build system which can parse a lot of tables and create contemporary tables about a certain task. So on and so forth. Combining all these structures become large, which is the whole document. And when we move to multi-document, which are connected by citations or co-authorship, then it becomes extensive context. So we will be using these contextual sizes as we were talking about earlier to drive our discussion of information extraction. And we'll be selecting some indicative examples of each of these information extraction tasks. And we'll be looking into and building some kind of discussion and conclusions. So first thing, we take the problem of reference string parsing. So as I introduced earlier, it's a short example of a short context. Reference string is essentially, as you see, there is a given example. It's essentially, this work was done by this person. It was published at this location. These are the page number and volume where it was published. So the idea of parsing is, given the text format, identify different entities which appear in this text surface string. So first, let's go to the model that we propose. We'll come back to see how we differ from baseline and what addition it brings to it. So here we have, I'm not sure if you can see the pointer. Never mind. Here we have character level embeddings, which pass to bidirectional LSTM, which goes and form character level word embedding, which is concatenated with word embedding, which finally goes to another bidirectional LSTM, which is word level bidirectional LSTM, which pass to some sort of feed forward network. It can be further passed finally for decoding to a softmax or a CRF to do a global decoding. So these are our component A, B, C, D, E. What we do is like present here result of each of these additions. There are a lot of numbers. Let's not go in the numbers. What we need to actually learn here is most of these components give some additional gain on top of each other. That is not these components add something to the modeling capability of this neural model in a short context. But the most important gain comes from the CRF layer, which essentially try to enforce the global decoding on the whole sequence, which is okay. This was the model that we proposed. This is called neural parser. It is compared against the state-of-the-art model at that time, which is parser. So again, there are a lot of numbers. What we need to focus on is the final F1 score and the relative error reduction. So there, it's not 21% relative error reduction as compared to 5 error points. One important thing to note is that there are certain fields, though, which the proposed model, that is neural parser, give decrement in performance. We have certain explanation for that. But again, instead of looking at all these numbers, let's look at what these numbers actually translate into predicting the tokens correctly, which was our original task, identify each of the label for the tokens. Those were the 13 labels that we were showing. So what neural parser gains over parser is the tokens which appear far from the start and the tokens which appear for longer duration. That means institution, because the name of institutions can be bigger. The name of conferences and the name of journals, these can be relatively bigger. So these things which appear farther from the start in the reference string, generally none of the reference strings start with the name of university first, they start with the name of authors. And the things which are usually relatively of longer length, like the 31st annual conference of some meeting of something. So the positive numbers are the gains, and you can see that the confusion between title and book title, these things are longer, also appear far from the start, semantically closer. The neural parser wins over it. There are a lot of analysis in the thesis, but overall the point is by adding character embedding, semantic embedding, that is the word embedding, and other source of information, in a local context, we can reliably provide model with enough information to model these nuances which are necessary for doing information extraction for relatively simpler task of reference string parsing. So our results show that classes farther from the beginning and which appear for the longer duration show improvement. At the same time, the classes which are syntactically and semantically closer also show improvement, because we incorporate character embedding as well as the word embedding, which help to distinguish these classes better. Whereas the previous model, which is the parser model, the baseline model, that only has character embedding and hence no source of disambiguating between syntactic and semantically closed classes. So in conclusion, for the short context information extraction task, if we are able to provide features which are semantically and syntactically meaningful, we are able to do information extraction reliably with just using sequence labeling kind of model. But as we will move further, we'll see that this statement starts to become weaker. So let's move to the next case, unless until someone have any question regarding short context information extraction. Yeah.
Just of curiosity, is there a basic difference between
mean, for example, if the author names, they're usually out of vocabulary strings, right?
Yeah.
And proceedings, I mean, this is usually a set of 100 words, right? I mean, some conference, some location, so fundamental difference between authors and the rest.
Good point. So the point is, if you use CRF, that's one of the good point of CRF because it enforces a global decoding. Sometimes even if author is completely out of vocabulary, but it's appearing in the start, it tries to enforce that it should be an author. That's one of the benefit. But the question that you were saying that the conference can only be few of the words, the data set that we worked on Quora and the Quora Plus, which we were saying there, it has English as well as German, something from humanities, something from different domain of computer sciences. So we try to have, it's a small data set, but we try to have a mix of a lot of different domains so that we don't overfit to certain kind of characters or word bias to just produce it better. But there is a lot of effort in producing global reference string parser, which is still an open problem. Okay, so we move to the type key phrase extraction. So the idea is, again, we have moved from small context to medium context. That means more than one line, a paragraph, or maybe few text lines. And here we are looking into two particular problems. The problems are basically both are of type key phrase extraction. So first we have to identify a key phrase, and then we have to type it among one of the classes. So in this particular example, which is a science IE task, we have three classes. These classes are process, material, and task. So we have to identify a key phrase of this type. And then the second example that we are taking of this same use case is we are given a sociology text excerpt, and then there is a name of data set, which may be a report from some government, and we have to identify the name of that report, which is a data set in that particular sociology publication. So we model both of these tasks as first you have to identify and then you have to extract. Though as we have all discussed it earlier as well during our prior presentation, that this text, like in this particular example, this can be seen as instance of the same class, but we try to put it this way so that we can make a more generic statement about this particular kind of information extraction. Okay, so first, as we had two models like CRF with features and CRF with word embedding or the neural model. So first we look at the CRF with a lot of features, handcrafted ones. So we have the term and the lower term, as well as the n-grams of the term, the part of speech. Orthographic features means different kind of additional characters added to the terms. And if that term appear in the title and the output of the previous token. Just wait for a moment, but there are a lot of things happening here. These things minus means that out of all features, those have been removed. So it's just with every feature except for this one. But what we want to focus is on this one, which if we go back to our first few slides, we remember that the CRF was giving the most of gain in the neural model as well, which was trying to just do the global decoding and stopping model from predicting various output at different tokens. The one of the audience also asked a question about. So the amount of gain you get by having this feature is huge, as you can see when this feature is included versus when this feature is removed. So next is for this. So in this task, there isn't enough data to train a neural model. The neural model which is trained on this task only has 300 documents. The neural model which is trained for this task produces result which is much worse than 0.4 F1 score by just using CRF based model. There are tricks to make this work for neural model, which has been later published. But next we move to the second task, which we are talking about, which has around 3,000 documents, which we tried the neural model, and hence we have results for neural model along with 3 sets of experiment. Before going to the neural model, let's discuss the setups. So the first setup is we perform subtask A and B jointly. So subtask A is, as we remember, identification, and subtask B is classification, that is the typing. And unified is that we have expert model for key phrase extraction. That means all the different classes, we collapse it into one class, and we just want to identify that class. And the third model is we have an individual model for each of the individual classes. So for both different data set, that is science I data set and the risk text data set, these are the results. So let's try to interpret the results. We see that in case of the feature-based model, the joint versus unified model, that means either if you take both class A and B prediction, both different classes, that is process material and task prediction, jointly or separately, they produce almost similar result, even in the unified or in the joint fashion. Whereas in the rich text model, which is entirely neural model, we have bidirectional LSTM, CNN bidirectional LSTM, CNN bidirectional LSTM plus CRF, which is all the model that we previously discussed, and CNN bidirectional CRF plus attention. We get much higher gain with using attention. Anyway, so the point is that multitask model here show lower performance and not a lot of difference. Whereas in this one, multitask models show much lower performance. And for task B, we see that there is a huge performance decrement when we train the individual model for science I task, whereas there is individual model perform better as compared to multitask model here. Okay, so there are 8 numbers and you can see all the differences in the number, but I have summarized the differences here. So 2 things are happening. There is the label rate and the cardinality. So for one of the data set, cardinality is very high. There are more than 1,000 of data set types, and you have to identify all the data set types. And for the other task, the cardinality is very low. There is process material and task. Similarly, the label rate for one of the tasks is very low. That means there are only 1 or 2 occurrences of the dataset name in the whole document, whereas there are many occurrences of process material task in the same line. So these 2 are varying factor, and based on these 2 factors, the models show varied performance in the unified or individual setup. So one of the points that we want to discuss is in the medium context, there is no such global solution, because depending on the cardinality of the task or the amount of occurrence in, because the medium context can be more than 1 line, but it can potentially be a whole paragraph. And if the occurrence is so sparse that it appears once in a whole paragraph, then the technique which applies to the task where the occurrence is fairly high is completely different. So that's one of the takeaway. And the second takeaway, much more interesting, which even founds our point more strongly, is the performance we saw here in both the cases for the multitask approach was much lower than the unified approach in this case, as well as for the task B. Whereas in recent results for a lot of tasks, it has been shown that multitasking approach shows reliably good result if both the tasks are related. Whereas we show it on 2 different tasks that the multitask approach usually, in this case, doesn't give good result. And when we find out why this is the case, the reason is that when we take longer context and the amount of label is not very high or the label is very noisy, then the model start doing classification based on the sideline information. Like if it has to identify which data set it is, it will see other terms like crime and population. So it will see that maybe it will be a data set related to crime and population, and all the data set which are ever in the crime and population, they start predicting that. When we force it to do multitask, that means identify the string and then classify it, then it start giving poorer performance. So it brings back to our point that as we move to medium context, the model start losing capability to focus on strict amount of information that we want it to predict a certain kind of thing correctly, which, as we were discussing in the global scheme of things, that as we move from smaller, that is the short context, to slightly larger context, which is currently the medium context, we already start seeing deterioration in the performance of the model. Does anyone have a question? Okay, so next we move to the third case, which is the full text key phrase extraction. That is example of a large context information extraction. So key phrase are the most salient terms in a document, usually used to index documents. So the task is that given the full text of the document, we have to identify top 5 or top 15 top phrases in that document. So previously we saw most of the techniques which were sequence labeling based technique. Here we present, because in large context, there have been a lot of technique which use both mix of sequence labeling as well as classification, or as well as feature engineering and weighting. So there are some unsupervised technique which usually are able to handle large text very reliably, but given a smaller text, they don't have enough statistics to generate for unsupervised techniques. Then we have certain supervised candidate selection followed by classification. Example of these techniques are here. And these techniques work equally good on large text as well as small text, depending on how these techniques are formulated. And we have been discussing the sequence labeling based technique, which all these are example of. We will be discussing one more of it, that is copy ironing, which is a strong current baseline for key phrase extraction and key phrase generation. So we'll be using it as our competitor for full text key phrase extraction scenario. One thing that we find out is, or one thing that we see in the full text key phrase extraction scenario that can be very good to have is ability to incorporate random walk as importance. The unsupervised technique that we were talking about, they do nothing. They just try to generate statistics of what words should be important because they appear together with a lot of other words, and they just use it as key phrases. So what if we can incorporate in a supervised technique these kind of ability and learn from the node specific features? This is the most salient gain which comes from the supervision. So why not we have this as well? And then use the neighborhood to enhance the node specific feature, because we have seen that the local context of the node is also important. So why not use some features of the nodes which are around the current node? So what we want to do is we want to incorporate all these things and come up with a technique which can do key phrase extraction better for the whole document. And that is what we propose by using a global and local model. So how does this model work? So first we see the formulation of graph convolution network. In terms of formulation, it is very simple. It aggregates feature of every node in the adjacency of a particular node, including the feature of the node itself, and then transforms it using some weight, which is obviously learned by some gradient. Then people came up with even a fancy way of doing the same thing, because in the previous formulation, which we just saw this one, you see all the edges are fixed because the adjacency of the nodes were fixed. People said that, why do we need fixed adjacency? We can make the adjacency as parameter and learn those parameter itself. These parameters will be function of the node pairs that these parameters are. So this became graph attention network. But the important thing that was missing in all these cases was all these were designed to do classification, and at the same time, they were not catering to any information which was global. All these parameters were tuned using the gradient, and gradient is essentially local based on the amount of feature nodes present in that batch. So what we introduce is first we generate the global statistics by using some kind of random walk, and then we enforce these global statistics to be coefficient of each of the node. This way, if you see in terms of like previous example, we incorporate the importance of each of the node by enforcing the node to be scaled, the feature of the node to be scaled in that way. So in this way, whenever the model learns, now this part of the model is frozen, and still we learn these things. So models still learn the importance between the pairs and all the things, which is the local importance of this node with respect to others. But at the same time, it still keeps the global importance of this node with respect to all the other nodes, which cannot be learned in a local fashion to make the ranking better. Once the ranking of node has been generated, to generate the multi-phrase key phrases, we use re-ranking. That means we sum over all the different tokens which appear in a multi-token key phrase, and then use that as the rank and re-rank item and take the top n. This technique is like used by a lot of people already. So like from Zhang et al. In Mike, in one of the system which is called Mike. So we are comparing with the copy iron system, which we said that is actually a key phrase extraction and generation, because it can produce one of the key phrase from the vocabulary or copy one of the things from the input which is not in the vocabulary, that is out of vocabulary word. So it has both generate and copy mode. Generate, yeah, sorry. So we have results for 5, 10, and 15, but we are just showing here the result for 15 key phrases. That means once the ranking is done, we take out 15 key phrases from predicted by our system and then test it across the gold label. Now we balance this whole table in these three groups. The first one is unsupervised one, which we show in the results were the very old methods, which were primarily based on statistics. You can see their results are relatively much weaker. And then the second set of systems are sequence labeling based systems, whereas in which one of the system is copy ironing. There is two run of copy ironing because in the original paper, the copy iron is provided to run only on abstract, and it provides reasonably good solution because abstract is small, and in scientific documents, it's a caveat or a feature. People can decide. Most of the key phrases appear in the abstract because abstract is also a summary of the scientific document. So that's why it works as a very strong system. And then we have the original graph convolution and graph attention network, and finally our proposed model. So yeah, the main comparison is between these two models because these two are kind of family of this model itself. So one of the question is like, why not just use the text rank score as one of the features in the graph convolution? So we do that experiment and find out that while using it as feature gives some gain, using it as a scaling give much higher gain. That is 0.5% as compared to 3% gain. And it also gives a nice formulation to text rank average node embedding, and it helps generates longer key phrases. And one of the weakness is that as compared to strong sequential model, in short context, this model doesn't work well because it is designed to work for longer context by incorporating the statistics of the whole graph in the learning method. So to conclude this section of full document context, graph-based model scales relatively better as compared to the previous sequential model that we saw in the large context. So before we move to multi-document context, does anyone have any question? Okay, so next we move to extensive context. That is a lot of documents connected to each other by citation or co-author, or connected to people by authorship and then co-authorship and so on. So this is extensive context, and we'll be still looking into the problem of key phrase traction, but from a different point of view. So this is not to say that this is a new model, but it's more like an application of how graph convolution network can solve a real life problem. So what is the real life problem that we are trying to talk in this particular extensive context? Usually most of the extensive graph are noisy or partial. That means there is an incompleteness. In terms of scientific document, there are paywalled site. That means certain scientific document don't have their publication text, or their metadata is partially missing. That means their bibtext is missing, or some entries of their bibtext is missing. So the question was that, can we use the cross document context? That means if we know what kind of document it is citing and still it's paywall, can we use that information to generate a better insight, or maybe do key phrase traction? At least we'll know how to index that document even when it's paywall. So then we just use an extension of GCN that we just saw in previous chapter, which we call multi-entity GCN. And we so first we see what co-authorship graph looks like. So there are documents which cite each other, and there is authorship between a document and a person. These are people node, and people can be co-author if they have worked on the same paper, or someone can cite a paper and then someone else could have worked on that paper. So this is a general citation graph, citation and authorship graph. So what we do is, to deal with this problem, we take the semantic scholar dump, we convert this into form of features and labels. So as we discussed, we want two kind of nodes. One is author node and one is publication node. So publication node is fairly available. For author node, we need certain kind of label for author node as well. So the label for author node is the venue where the authors publish. And for the publication, the labels are key phrase, because ultimately we want to do key phrase extraction. So these are our two entities and these are our two labels. And as we discussed in graph convolution networks, there are two things that graph convolution network do really good. One thing is aggregating features from the neighborhood, which is the case we were talking about. Suppose if the publication of the text is missing, you can aggregate the feature of all the nodes around that text, that particular missing text, and you will get the text of this thing. Just hold for a second that it doesn't sound like, why would the text, if you just aggregate the text, it will become the text of the missing node. And then if the attribute is missing, then we know that the graph convolution network applies a kind of label regularization on the label of neighborhood nodes. So even if certain attribute is missing, you can apply partially that attribute from different neighborhood nodes. So this brings us to the experiment. So what we do is we remove k% of the nodes from the graph, and with the publication for k% of node, we remove the publication text and we try to predict the key phrase for those nodes. So now, as we are saying, that one way is to just average all the text and of all the nodes around the neighborhood, and you get the text of the missing text. And everyone will be like, that doesn't make sense. And that is what happened when we use linear regression or RNN or CNN based model, because these models will just, so what we do in these models is, because if there is no text, there is no feature, these models cannot predict any key phrases. So we average all the text around for all the neighborhood nodes and pass through these three models. And you can see the performance of these three models is really low, because the average of text of all the neighborhood node doesn't define a node's text. But the idea is, because of the because of these two property, and because there is a weight matrix, as we discussed earlier, which is learned based on gradient, while training, the graph convolution network learns to recognize which features of the neighborhood node are actually related to the feature of the current node. And hence, when we use GCN or this multi-entity GCN, which has both author and publication type of node, we see that there is reasonably better performance as compared to all these three basic model of aggregating text together. So to conclude this part, partial incompleteness of data can be handled by graph convolution network gracefully, because it works on the idea of label regularization and as well as feature aggregation. And MEGCN can embed multiple entities into the same space. So even if certain entities are missing, you can get other information from co-occurring entities. That is why we see a small but consistent gain when we use MEGCN in addition to GCN. So as we have moved from small to medium to large and to extensive context, so one thing we are trying to show is like sequential model can be reliably replaced with graph-based model. We didn't want to say graph convolution model itself only, but graph-based model. But also that sequential models start becoming weaker as well. As we remember from the last time, it's not to say that the graph-based model cannot be used for sequential task or for the small context. In fact, sequence is a simplification of graph. You just remove all the nodes and you can make a sequential model out of it. But the idea is that in the current formulation, the kind of sequential model and the graph model that we use, this holds true. Yeah, and that's to conclude.
For the medium context, right? Medium context, there was a shared task that you participated in, right?
Yeah.
You didn't show the results of
the I have extra backup slides. It's here. Yeah, it's.
Can you comment on why your proposed method is not
Okay,
well,
so let me tell what all methods are.
0.27 versus 0.43, right?
Yeah, I can tell all the methods what's happening. So from here to, I think from here maybe to this point are all method based on CRF and feature rich models, which like our model is as well. So it's reasonably well as compared to all the other CRF based models. These models, especially the first one, is a model which is same as the first model that we did, which is neural parset kind of model, character embedding, word embedding, bidirectional STM CRF. But it comes from a team LNAI. What they did is they additionally trained a language model on all the scientific documents they have in their repository, which is a lot of documents because they just deal with it.
So maybe that's what you should be looking on, right? Those are the ones that's going to give improvement. Like you're not doing that kind of thing for all of your work here, right? So are you missing the important thing and and working on less relevant issues?
So after this, I think this model came from their Elmo-based extension of sequential modeling, and then they did bidirectional language model, and then translated. Then like slowly the domain moved to BERT. So now it's pretty much assumed that if you start any basic, you don't use character LSTM, word LSTM, CRF model anymore. People start with BERT, CRF, or BERT itself, and that works. So, I mean, even there, this model would be beaten by plain vanilla BERT today.
That's not my question. The question is why are you not going that direction?
So that direction
is even before that. I mean, like your neural parsing for the reference string parsing. Right?
Yeah.
For this medium context, this is just doing CRF, right? That's not even neural CRF work, right?
Yes.
So why this switch around, right? And this has nothing to do with graph-based or sequence-based. So why, like you suddenly change one to another with no really good reason, and just put everything together in one thesis, right?
So we tried neural parset on this one, but without having. So the neural parset also has like 100 millions of reference string, which we just, because reference string is easily crawled out by using patterns from dump of data set. So we just use it and we just trained fresh word embedding. We use that word embedding in the neural part set, which is written in the report, which gave us which helped us to make neural parset word even when the number of reference string we have, the label examples were only 1000. So we were able to make neural parset work because we crawled out a lot of reference string and we used it to train word embedding. To train a language model for this one, it would have required to carefully crawl out excerpts which talk about process material and tasks from certain type of scientific document and certain thing, which would have been difficult. I mean, it's not, I'm not saying it's impossible. It will just,
That's why it'll give you
time to-
likely improvement, right?
Yeah, I agree.
Perhaps, might be better if you explore this dimension. Anyway.
Yeah, I agree. But I think that's what I was saying, that this is like improving the language models. And today everyone will say, oh, BERT, take BERT.
There's even better things to do. Anyway.
Yeah, Roberta or, yeah.
I mean, I also didn't find at the very last conclusion, you mentioned about, I'm not really sure, like based on the evidence provided in the thesis, right, that you have thoroughly examined. You mentioned like as you go towards larger contexts, graph-based model is better than sequence-based model.
Okay.
Yeah, I'm not really sure. It will be a nice conclusion, but I'm not really sure you have evidence like you've done, experiments that you've done, right? Could support this this assertion.
So
I'm not really sure.
So I would like to make a point on.
You didn't show graph-based model on like simpler, smaller contexts, right?
Yeah. So I would like to make 2 points on it. So my first point is this. There is 2 run of copy RNN. This run of copy RNN is, as the authors say, that you take the abstract and you run and you still get key phrases, because in scientific document, abstract is a good summary of scientific document, and most of the annotation guideline actually start that go through the abstract, tag the key phrases, then go through the document, tag the key phrases. So it usually is how the domain is. But if you run it on the whole document, this is just take copy RNN, run it on the whole document, you see the performance is really bad. So we are not saying that this is the way to solve the problem, but we are saying that this model is inherently not capable of.
What does copy RNN got to do with my question?
This is a sequential model.
Have you investigated like a graph-based model, right, on smaller contexts? You know what I'm trying to say? Your graph-based model was only used in large contexts. Right?
Yeah.
But I said wouldn't be effective. No. Or you comment its effectiveness on the small context. They were small context, you should use sequence model, and large context you use graph-based model, right? That's what you said.
No, I didn't say and vice versa. I said sequential models.
What is the? Can you show the statement?
Yeah, the statement is not. This is the final conclusion is also
this one.
So it actually supports your point. It says that graph-based model can be simplified to act like sequential model. So graph-based model are like.
So yeah, a sequence to me is just a graph
with links removed.
The edges on.
Yeah, I agree.
So then, if that's the case, then what's
the
different? What are the differences between all these things? Right, if the sequence model is a special case of the graph model,
yes,
then there's not much.
So the point is this:
saying something else.
Right. But I mean, I agree to that point. But for that purpose, like all the model are simplification of some function of.
No, you probably should be saying that for small contexts, sequential graph is enough. For a large context, a different graph.
So
required or
so
something.
how I would like to say is like this way. LSTM has one connection. When people said that LSTM doesn't cover all the equal thing, they form bigger connection by having skip connections or attentions. Those things, if you think, are the additional edges. Those are the graph. People are not calling it graph, but those things are additional edges that we are augmenting because we cannot capture the additional points. So what
In
we
that
are
case, the sequential model is not enough either.
exactly, because it doesn't capture, it cannot remember, because there is information theory bottleneck. If you keep averaging information at many time steps, at one point you are going to saturate. So if we have something like a graph which has one node for each of the thing, then it's not going to saturate. That's the overall idea.
Okay, but I'm not sure. Your message is not very clear. Right? It's not very clear what you're trying to say.
Okay.
Other comments with respect to writing, which are problems with
Yeah.
Yes, okay, still, so after the presentation, there's a public Q&A part there, and then there's a closed session, right? So devotees still have public questions before you. All right, then maybe you'll go